much for joining us tonight. I'm really excited for this event. We actually tried holding it a couple months ago, but of course we had a global pandemic to kind of put the squash on that. So huge thanks to our great presenters tonight, and we'll jump right in. So our topic tonight is quantifying climate change, and this has been something that I've really been interested in personally for a long time, but always been a little bit maybe intimidated by just sort of the scope of it, how much work really goes into understanding it at a real level, not just talk about it, reciting facts that you hear on TV, right? So I wanted to take a deeper dive into the data, and as we were going through different topics for potential forums for GreenHomeNYC, which I'll explain in a second, this just seemed like a great opportunity to get other experts to explain it to me. So we've got three great panelists here tonight. But first, I'll just give you a brief introduction, I guess, to me as well. I'm Mike Bose. I'm an associate engineer and DG ombudsman at Sustainable CUNY, where a lot of the work that we're doing right now involves breaking down barriers to energy storage permitting in New York City. By night, I'm a volunteer here at GreenHomeNYC, among other things. And a little bit more about GreenHomeNYC. We're a community-oriented and volunteer-run organization founded in 2002. We've had over 150 volunteers through the past, through our time as an organization. We are a nonprofit. We hold monthly career and forum events, usually in person, where we get a lot of community members come in, learn a little bit about sustainability, do some networking, and it's really been, personally for me, a great opportunity to be learning more about things that I never kind of would have been able to learn in a vacuum. So it's been a really great program, and thank you all so much for joining us. Our speakers tonight, we've got Susan Golden, Louis Ortiz, and Peter Marsters. They've all got just crazy credentials and backgrounds. I wanted to write a little bit more of it down here, and explain it, but I'll just let them kind of get to it as they go on. But we're so lucky to have them here to share their expertise with everybody. And what we'll be doing, we'll be passing off to them for their presentations. For the once everybody's done, we'll have like 15 minutes or so to go through some Q&A. So if you have any questions, drop them in the chat box, and we'll read them aloud afterwards and give the panelists an opportunity to address any of your questions. So let's just jump right into it, you guys, and I'm going to hand it over to Susan.
Great. Thank you, Michael. Let me just start my screen sharing here and bring up the presentation. There, can you see it? Terrific. So tonight, you asked, we're discussing quantifying climate change and solutions for New York City, and I'm going to be presenting you plenty of numbers tonight. We're going to be looking at the effects of climate change on the city, and as we dig out from this global medical crisis, I hope that we will accelerate our efforts on our other global crisis, of course, which is longer and more prevalent, hopefully, which is going to be, well, I'd like it to be shorter, but I want the COVID-19 crisis to end very quickly. So let me just go on and start my presentation. We're going to look at the environmental effects of climate change and some of the solutions that are available to us here in New York City. So first of all, let's identify the region. I'm talking about New York City, but as you know, New York is not an island in the middle of the ocean. Well, okay, it's a few islands, but it's in the north side of a bay, at the mouth of a river, and on the coast of a large continent. And so when we talk about climate or weather, we can't talk about just New York City itself. We need to look at the region. And one definition of the New York City region you see here is 31 counties in 4 different states. but most of the data you will see in this presentation is from the 5 boroughs of New York. So I'm going to take you through some of the effects of climate change on New York City, and we'll talk about weather effects, sea level rise, coastal flooding, and we're also going to talk about some of the solutions. I won't have time to get into it in a lot of detail, but try to put you in this right direction for more information. So let's start with the weather effects. I'm going to talk about the weather trends, as well as cold weather and heat waves, and I'm also going to talk about precipitation trends and heavy downpours and droughts. So let's start with the source of our weather. That's the jet stream. And we found that over the years, the jet stream has, they say, a deepening and a slowing down of atmospheric waves. In other words, the jet stream no longer travels in as straight a line in the mid-latitudes as it used to. It tends to wave like this. And the changes in it are creating more what's called atmospheric blocking events, and that's a stalled high pressure system. And they have found that these stalls are related to the width, latitude, and strength of the jet stream. And some of these deep bends in the jet stream also allow that bitter cold polar air to come down, particularly in the winter. And that's why over the last few years, we've been having, despite global warming, some freezing days in the middle of winter here in North America. But the models say that the frequency and duration of that polar weather is not going to change much in this region over the next century. There'll be other parts of the world that are going to be feeling it. That does not mean that the polar weather is going to stop. We'll still be seeing it, but it shouldn't increase in duration or strength. And as you probably know, what is happening is our annual temperature is going up. And these are observations from Central Park, where we have temperature and other data dating back to 1900 and a little farther. That's the black line that you see on this graph at the right here. And the far right of the graph is the projections from different models. And scientists feel that we will end up somewhere in this peach-colored, salmon-colored, I don't know what color you want to call it, central range. And they use statistics to determine that. Now, people don't come up with this out of the blue, just so you understand that virtually all the data in here that's been a projection is based on multiple global climate models. They either use a set of 35 of them or 24. And they also use what's called a representative concentration pathway, which pretty much, to put it in a nutshell, it's either a medium emissions that we're putting out, we've reduced some of our greenhouse gas emissions, or a high emission scenario, RCP 4.5 and RCP 8.5 respectively. I'm not going to get too much into those things, but scientists have put all these numbers into models, and they've come up with, clearly you can see here, a projected increase in temperature over the course of this century. Already we've seen a temperature increase of 0.2 of a Fahrenheit degree per decade in Central Park over the last century. So if the weather is warming up, it's warming up in the winter and it's warming up in the summer. So in the winter, we're seeing, again, these are temperature readings during the winter months at Central Park. And you can see this graph is the number of days below freezing. That's 32 degrees Fahrenheit. And we now have 22 days fewer than we did in 1900. And that goes a long way in explaining why we can't ice skate on a lot of the ponds all over the New York region. We have fewer, colder days than we used to. But of course, the winter isn't the only thing warming up. The summer is as well. And this is summer data. The black line, again, is Central Park. And that's a black trend line that goes through it. And then the red dots and line are data from LaGuardia Airport, and the blue is from Kennedy Airport. And you can see trend lines for each of them. So Central Park temperature in the summer, it's still an increase of 2 Fahrenheit degrees. And Kennedy is an increase of 0.5 Fahrenheit degree, and LaGuardia is an increase of 0.7 of a Fahrenheit degree. I do want to put a caveat on that. The observations we have from both of those airports have not been in long enough of a duration to be statistically significant yet. But clearly, you can see that all of those lines have positive slopes. And as a math teacher, that means things are going, an ex-math teacher, that means things are going to be increasing as we move into the 21st century. So as temperatures get warm in the summer, if they get warm enough, we end up with a heat wave. So what's a heat wave? Well, that's 3 or more days with temperature above 90 degrees Fahrenheit. So some scientists and some of the models chose a baseline of 1971 to 2000, and I've seen baselines that go back to 1900. So this is actually already where temperatures have started to increase. And they've seen that we have, on average, 10 days a year that are above 90 degrees. But they're expecting by 2080 to have 24 to 75 days above 90 degrees Fahrenheit. And those are indications of percentiles from a normal average. So pretty much we can count on 2 times, 3 times, 4 times, even 5 times the number of days above 90 that we see now by the end of the century. And that doesn't bode very well for a comfortable weather. So just a quick bit on heat waves. In the data seems to point that it's every 20 years, the heat waves will occur more often. We'll have one additional event. They're going to last longer. So as we proceed into the early half of the century, there'll be 2 days longer every double decade. But towards the end of the century, they might end up being 10 days longer than they are today. And that is one reason why we may not have more events, because if the events last long enough, they will blend into another. And of course, to make it even more difficult, they're expecting that the average high temperatures are going to go up from 93 degrees early in the century, like now, and they'll go up another 2 to 5 degrees by the end of the century for these heat waves. But I don't want to spend too much time on this. Dr. Ortiz will be speaking of them when I'm done, I think. So I don't want to steal his thunder, but I do want to talk about other precipitation. And we'll move on. And it turns out that here in the Northeast, we have an annual precipitation amounts of 43 to 50 inches. And that's in both rain and snow. And again, these are data from Central Park, and you can see how the data oscillates. It's not a nice narrow band, but it varies quite a bit. And the precipitation increase, again, we have a positive slope on that trend line, and we've seen 0.7 of an inch increase per decade since 1900. They're predicting, the models are predicting up to a 15% increase by mid-century, and that will go higher still by the end of the century. But I do want to say that annual precipitation amounts vary significantly, as I mentioned a moment ago, and it's very difficult to predict it. I'm going to explain that in just a moment. One thing we have seen without a doubt is that the heaviest 1% of daily rainfalls, so the number of days that we have really had drenching rain, has increased 70% between 1958 and 2012, particularly here in the Northeast, as you can see. And this is due to both large and small weather events. So large events are cyclones, which here are actually hurricanes or nor'easters, and they're large regional events that last for a couple days, and we see a lot of flooding often. And then the small weather event is considered a thunderstorm where, as you know, there might be flooding in one borough of New York and the other borough might not even have gotten wet. So both of these events cause the heavy downpours that we see, and the numbers of those downpours has increased significantly. So I mentioned unpredictability though, and this is the difficulty, and this is the one place in this presentation where I'm describing the why. And one reason that we're having trouble with predictions for heavy and rain and precipitation is the complexity of the weather patterns. Here in the Northeast United States, we have several air masses that tend to collide. It's also the complexity of the coastline interactions. And what I mean by that is not only the fact that the air and atmosphere coming off the ocean is going to land, but here in the New York City region, we have an interface. So an afternoon onshore breeze doesn't just blow over the plains, but it hits, for example, the high-rise buildings in Manhattan. And so if you're going to be trying to model the effects of that onshore breeze, you really have to model the effects of that breeze and the interaction to essentially that wall of concrete that it hits. Another reason for difficulty in predicting precipitation events is the model scaling. And most global climate models have scales from 100 to 200 square kilometers for their grids, and those are very large when you're especially when you're trying to look at thunderstorms. So the cool thing is, if you're at all into computing, they're coming up with some amazing new dynamic scaling models to try to compensate for this. And so better models are emerging all the time. And the last reason for difficult predictions is we don't know what some other atmospheric effects will have, what effects those effects will have on the future. And one thing they're considering is the North Atlantic Oscillation, and that's a atmospheric pressure between Icelandic low and the Azores high, and it influences climate patterns in the Northern Hemisphere. But enough of this water. Let's dry things out a little and look at the drought. So studies show that they're predicting that we're going to have more droughts, short-term droughts, which are just a couple weeks or months, and we should see two times more often than we do now, and possibly 5 times more often by the 2080s. And but New York City, which you see on this image here, is really down here, and we don't get our water from down here. New York City gets its water from the Croton watershed and the Catskills Delaware watershed. So in the last 5 years, they've done some analysis of those areas using particularly tree rings, and they've found that there have been 8 long-term droughts that have lasted 5 years or more since the 1750s. So we have, the last one that we've seen has been in the 1960s, and we have had some long-term droughts, but scientists and the models are showing that droughts are not the biggest concern for the New York metropolitan area. So that was a quick run through of both temperature and precipitation effects of climate change. And now I want to talk a little bit about sea level rise. Sea level rise is ongoing, and it's going to continue well beyond the end of the 21st century. So while the other effects, it's clear that sea level rise is going to continue on for possibly millennia. So this graph is from Rutgers University, and this bottom line here is sea level market 1920 average. This black line is the global sea level rise since then. The brown line is high gauge data from New York City, particularly Battery Terminal, and the green is the New Jersey shore. And you can see how both New York and Jersey are experiencing faster than average global sea level rise, Both global warming and sea level rise do not affect the planet, the entire planet, in a uniform manner. Each of those have different effects on different areas depending on where you're looking. So, but let's quickly zoom into that battery tunnel data, and here you have it. And you can see that sea level has already risen over a foot in the last century, and they have a trend of about 1/10 of an inch per year. And since the end of the 20th century, that's 1993, they're seeing an increase, even a faster sea level rise. So that rise is due to several reasons. And one, which is, I think, so cool, is the thermal expansion of the ocean. The air isn't the only thing that's warming up, the ocean is too. And as it heats up, like everything else on the planet, it expands. And so that's one reason we have sea level rise. The other is what you've heard of, which is ice mass loss, and that's particularly from Greenland and Antarctica. I'm told that it's the western ice sheets of Antarctica are actually having the biggest effect on New York City, more so than Greenland, and it has to do with gravity, and it's very complicated. And the other reason, though, that sea level is rising is that there is a vertical tectonic motion, and North America, along with other places, is the plates are moving up and down. In some areas, not New York City, the land is subsiding because of groundwater withdrawal. But in New York, it's just the fact that those, from the last ice age, those glaciers that have receded, the continent is still trying to adjust. And if that's gone on this long, imagine how long it's going to take for a sea level rise to go through a complete cycle. But with sea level rise, of course, we have increased risks. Salt marshes could be turning into tidal mudflats. There's beach erosion, saltwater intrusion, and land inundation. I don't have time to go into all of them, but I do want to talk about coastal flooding. There's two types of coastal flooding. And some scientists, and we've seen that this can be some of the most devastating effects of climate change. This happens to be a picture of Superstorm Sandy, and many of us have lived through that and the effects that it had. So here's some numbers. This is a map of a 100-year flood event. The purple areas on this map are areas that storms already flood. And you can see here by the legend that they expect the flooding to progress inland with sea level rise. In the 2020s with a 10-inch sea level rise, the green is the 30-inch sea level rise, et cetera, et cetera. And while they're showing you 90th percentile, which means this is the high of what they predict, those, we really need to use this number for planning purposes rather than a lower one and take risks. Because as anyone who was here in 2012 knows, that coastal storm flooding can damage thousands of homes, cause billions of dollars of property, ruin miles of roadways, sewers, wastewater treatment plants, as well as other infrastructure. But there's another type of flooding that's accelerating around the world, and it, in New York City is no exception, and that's what's called sunny day flooding. And that's where the tides have become so high that they've just gone off the beaches and off the banks, and they're now flooding roadways and ground. And here you see two pictures of very recent high tides, and you can see on this slide that since 1955 to 84, we used to have 32 days a year where we had some sunny day flooding. And from 85 to 2014, that number pretty much doubled. And there is no storm or anything that caused these other than an extremely high tide, and it's happening all around the world. And so here's the New York City panel on climate change. They did a map on monthly flooding. That's another word for it. And again, it's showing 90th percentile, so that's the highest it would get. You'll notice there isn't as much blue. We don't have that much present day sunny day flooding. And the models indicate that it shouldn't be a widespread problem until the second half of this century. But there are the lowest lying areas of the city, including down here, Brooklyn and Queens, and then parts of Staten Island are more susceptible to this. So all these environmental effects of climate change have impact on many different aspects of our lives in New York City. It's going to impact health, food, housing, utilities, infrastructure, as well as emergency preparedness. So I'm just going to literally touch on some of these impacts. I have other presentations where I can dive into more detail on these things. But climate change does affect health in all these different ways, particularly the heat is going to affect people and the elderly. There's more allergens in terms of pollen. Plants love the warm weather, and so there's more pollen being generated for a longer period of time. So if you have a pollen allergy, I feel sorry for you. It's not going to get any better. And all these other impacts of health as well. Climate change also affects our food supply in many ways, and while we don't have that many farms right here in New York City, we certainly get our food from the general region, and we need to make sure that that's safe for us, and we have a steady flow of food as well. And of course, there's damage from coastal flooding. These are pictures from Sandy. The right side is from Rockaway, where all those houses burned down. And the left just shows how emergency vehicles had trouble navigating. And of course, this coastal storm flooding causes infrastructure damage, wastewater treatment damage, drinking water contamination, a loss of power, loss of homes, loss of emergency services. and of course, most devastatingly, loss of life. So we really need to do something about this, about climate change, in order to try to avoid the worst. And the two ways that we can solve this are to adapt to changing climate and weather, because we have no choice. We have to adapt and change some of our ways and our plans. And we also have to mitigate global warming to try to reduce the severity of it. So very quickly, we need to adapt with public policies and actions. New York City is starting to do that. They've been working on it for a little bit with their climate resiliency design guides. They have a Flood Help New York City, and they talk about it on their website. And I'm guessing that several of you probably know more about the policies than I do. So I'm not going to go into them that much, but we also have to adapt from a private perspective. Between community groups need to pull together, building owners need to pull together, and we do need to try to change our lifestyles a little bit, and I can go into that in more detail another day, but we do have to adapt. I mentioned the Empire State Building. Just to give you an idea, they went through a major retrofit a number of years ago, and they now use 38% less energy than it did in the middle of the century, which is pretty amazing. So it can be done, and imagine if every building in the city went through a retrofitting like that. And the other piece we have to do, of course, is mitigate global warming. And everyone here, I think, knows how we need to do that, and that is we have to stop emitting greenhouse gases. And this brings me to the solutions part, and for this I'm going to draw a lot from Project Drawdown, who presents these solutions. And drawdown, they define as the point in time when the levels of greenhouse gases in the atmosphere stop climbing and start to steadily decline. And we need to get there soon. The results of that project call for 3 areas of action. In order to reach that, we need to reduce our sources. In other words, we need to bring our emissions, carbon dioxide and other greenhouse gases, down to 0. We need to support sinks. And so far, research shows that the technology is not there for man-made sinks. We need to absorb as much carbon as possible. And in order to do it on the scale we need to protect and enhance organisms that perform photosynthesis. It's one of the best ways we have for pulling carbon out of the atmosphere right now. And we need to improve society by fostering equality for all. That includes healthcare and education, because as people, the more people know, the better choices they'll make. That's one of my philosophies, and that's one reason I do what I do. And a benefit of that is actually that we will remove some greenhouse gases from the atmosphere. So very quickly, the biggest sectors that are greenhouse gas emitters are electricity, food generation and land use, industry, transportation, and buildings, all of which we have here in New York City, and we must make progress in all of them in order to try to reach that drawdown point. And if we can do that, we need to do it by mid-century, or we're going to have those that global temperature rise go up higher than 2 degrees Celsius, and we're going to see some catastrophic changes to the planet. In order to bring those emissions to 0, we need to shift away from fossil fuels, we need to enhance efficiency, and we need to reduce our waste cycles. And Project Drawdown goes through a pretty good description of solutions and how they compare them in their Drawdown Review, it's called. And I don't have time to go through it all, but since you wanted numbers, here are some numbers. And so what they've done is they have taken each of those sectors, electricity, food, industry, transport, and buildings, and they have said, if we shift production, for example, we can remove 163 to almost 400 gigatons of carbon dioxide equivalent from the atmosphere. And by enhancing efficiency on our electricity production, we can remove another 35 to 45 gigatons of carbon dioxide. So they've done that with all of these. And I'm going to just very quickly, this is the Project Drawdown Presents Solutions, 80 different solutions of technology that's here. These are the icons that they have for all 80. They only considered existing technologies. We can do this now, today. We have these technologies. There are emerging technologies, but these are the answers that we can start with. And Project Drawdown did an excellent job of not only analyzing the carbon emissions, but also the economic aspects, and they made sure not to double count numbers. So very, very quickly, the building solutions, these are the 16 they offer, just to give you an idea. We need to find alternative refrigerants. CFCs and HCFCs are 1,000 or more times more potent greenhouse gases than carbon dioxide. We have to do something about that. They also suggest biomass for cooking. That does not pertain to us here in New York City. That's more for developing countries. Building automation systems, building retrofitting, and district heating are all alternatives that we can look for here in this city. And these solutions fall under one of these three categories. They're either shifting energy sources, enhancing efficiency, or addressing refrigerants. And this is just a look very quickly of one of their solutions in detail, dynamic glass, which is like if you have those sunglasses that change, or regular glasses that change to sunglasses. I think they call them transition lenses. That's kind of what they're talking about here. And I just want to point out that they present numbers. The leftmost number is the gigatons of carbon that we can remove from the atmosphere. The middle number that they present is the net cost to implement the solution. And the number on the far right is the net savings that we can have over 30 years of using it. And they present this type of information for all their solutions. And I highly recommend that you go and study that. And I can speak on that in more detail at a different time. But the bottom line for all these solutions is that we as a global society have to adopt the United Nations Sustainable Development Goals. I'm a big advocate for this. Right now we're talking about climate action. We have to be respectful of biodiversity, both on land and in water. We're looking at sustainable cities and communities. We must learn to live in a more sustainable manner with responsible consumption, etc. We need equality for all. We need clean water for all, etc. And this is how we're going to move forwards in the future so that future generations, my children, I'm about to be a grandmother in a few months, and I want my grandchild to have the type of life I've enjoyed. And already they're not going to be able to go ice skating on the ponds. And I'm wondering if they're ever going to get to go skiing at the ski resorts here like Hunter Mountain, like I did growing up. But anyway, that's my opinion, and I'll stop with that. I think now's a good time to quit. I just wanted one last thing. I'd like to give you some sources that you can find more information. This is a very new report, 2019, the New York City Panel on Climate Change. It's from the Annals of the New York Academy of Sciences. Extremely detailed 300-page report. And of course, you can go to drawdown.org is where you can find about Project Drawdown. I recommend looking for Drawdown Review. That's their newest document that they released in March. And if you want more information from me, or you'd like another presentation or something, you can contact me at sgoldeneducation.com. And with that, I'm going to stop sharing my screen and give it back to you, Michael. Thank you.
Great. Thanks, Susan. Wow, that was a great deal of information that you really managed to compress there in a short period of time. Bravo, your teaching acumen definitely showing through there, and congrats on becoming a new grandmother. We're now going to pass it off to Louis Ortiz, who's going to take a really deep dive into the physics and modeling the effects of climate change in urban environments. Louis?
Thank you, Michael. Let me share my screen real quick. All right. Well, thank you for having me, GreenHomeNYC, and super happy to share some of the work that we've been doing. Today, I'm focusing on sort of demystifying or explaining a little bit of the physical processes that sort of determine how climate interacts with our cities, and how the way that these physical processes exist in the city determine the kinds of impacts and where and who and the types of impacts that we see, with a focus mostly on heat, which is by far the most clear climate change signal that we have. So a little overview of my talk today. I'm gonna do a very, very brief overview of the global climate drivers, sort of following up in a very coincidentally nice way from Susan's talk on some of the emission scenarios. Then we're going to move on to talking about cities and what makes a city different to basically anything else that's outside a city in terms of how atmospheric processes happen. And from there, we're going to move on to when we introduce climate change into that city atmosphere system, how it sort of changes things or intensifies some processes or making some other processes less important. So let's start with global climate drivers.
Sorry, Louis, really quick. Seems
Sure.
if you're advancing slides, it's not quite showing. If you're in such a presentation mode, it might not have carried over if you started that.
Let me.
So it might have shared the application window instead of the your screen. Sharing screen might resolve that specifically.
Sorry about that. Let me.
Please, while he's doing this, just if anyone has any questions, please, you can text them to Jenny Nicholas. She'll take all the questions and bring them over to the speakers later.
Right. Maybe this is better. I guess the full screen is a problem. Where's the Zoom? Share screen again. All right, is that better? Can you see the transition between slides? And
Very good, very good.
awesome, thank you. And thanks for pointing that out. So here's where I left off. So let's talk a little bit, and by little I mean very little, about some of these global climate drivers. In general, when Susan was talking about these emission scenarios, RCP 4.5 and RCP 8.5, they're sort of defined by the net effect of greenhouse gases on how radiation is transferred in the atmosphere. And they're defined in sort of very broad average over the whole globe levels. So what you see there is sort of that net radiative forcing throughout the 21st century at a global scale for each of the two, sort of the medium and the high emission scenario. And they're called like that generally, but it's not just medium scenario, emission scenario. As you see, it sort of tapers off after sort of halfway through the 21st century, whereas the 8.5, which we call the business as usual, kind of keeps increasing sort of forevermore, essentially. So essentially what we're showing here is the net energy gain in the atmosphere due to the composition of the atmosphere itself. So what this number essentially is the difference, or subtracting from the incoming solar radiation, what actually gets reflected and sent back into space. So that sort of net gain is what we're sort of talking about here in a sort of instantaneous, simplified way. And this net gain, or the amount that gets transferred back to space, gets determined by the atmosphere, like by the chemical composition of the atmosphere. Essentially, what we all know about greenhouse gases. And the reason they work like that is because much like a piece of wood or your phone is sort of opaque to the visible spectrum of radiation, the red, green, blue, and all that. These gases are opaque to other spectrum of radiation, for example, the thermal or in the infrared spectrum of radiation. So that radiation, instead of being emitted back into space, gets sort of trapped in the Earth system. And that's why you get that warming effect. In effect, there's more and more energy getting accumulated. And as the atmosphere gets warmer, it sort of triggers the release of some of the other greenhouse gases. One of the very important ones is water vapor, which has a much higher it's much more opaque than even carbon dioxide, which we talk about. So it gets a little bit warmer, more water vapor gets into the atmosphere from the ocean or other sources, meaning that the atmosphere's capacity for holding heat increases, and in turn, that means that more water vapor gets evaporated. It's sort of what we call a feedback loop. So that's sort of what we're talking about when we're talking about these global climate drivers and all these processes and how they impact the climate around us. We focus a lot on carbon dioxide because it's sort of the first domino in that loop in terms of how humans come into the equation. So now we know a little bit about how global climate and Susan did a really good job about telling us a little bit about what all that means in terms of the increase in temperatures over long-term periods of time. So let's talk a little bit about what makes a city different. We talk a lot about these impacts of climate change. We talk about climate goals of 2 degrees Celsius, 1.5, but all these goals in general are very globally focused. But as the previous talk mentioned and showed, the impacts of climate change are not sort of a global average that everyone experiences. They vary, and they can vary significantly from place to place. So in order to understand how cities are different, we first have to understand how energy moves in the Earth system, and more specifically, how it moves at the surface of the Earth. In the most generic terms, you have some level of solar energy, which I call here F incoming. And then we have some outgoing level of radiation. And the difference between these two is essentially what the surface absorbs. And everything that makes a city different has to do with how it modifies that outgoing radiation. Of course, the city doesn't modify the amount of solar energy coming in, although it can modify the composition of the atmosphere around it through pollution. That's sort of complicating the equation a little bit more. So let's talk a little bit about that energy that gets absorbed into the surface. So part of it comes from solar radiation, and part of it gets out into space. Some of it gets reflected back, and some of it gets emitted by thermal emissions. And by thermal emissions, it's sort of a similar way to how your broiler in your oven transmits heat, just by the difference in temperature of a very hot element compared to another colder element. In this case, the colder element being space. So what happens to this absorbed radiation that incides on the surface? Well, 4 things can happen. Number one, some of that heat gets conducted further into the ground. Number two, if there's water in the surface, some of that energy goes into breaking the bonds between the water molecules in that soil or in that surface and evaporating it. And some of it goes into increasing the temperature of the air around the surface, what we call sensible heat flux. And some of it just gets stored and released through some of these other means over time rather than immediately. And what I'm showing there in that figure is sort of the typical daily cycle of these energy fluxes, where the black thick line is the net amount that is absorbed by the atmosphere, by the surface. The red line is that sensible heat flux. So essentially it goes into increasing the air of the temperature around it. The blue curve is the latent heat flux, which is what goes into evaporating water. And the brown line is what goes into the ground, essentially. And here the convention being that if it's going into the ground, it's negative. So that's why the line goes below 0 there. And you can very clearly see that it sort of reaches the red and blue lines as it gets hotter through the day. It reaches a maximum, and then as the sun comes down, it starts going down to a minimum, which is slightly negative. So I like to introduce this quote from Lord Luke Howard, who wrote The Climate of London in 1883. And he said that, thus, under the varying circumstances of different sites, different instruments, and different positions of the latter, we find London always warmer than the country, and the average excess of its temperature, and I'm always blown away by this number in 1883, 1.579, 3 degrees, 3 decimal points of precision there. So there's something about cities that makes them warmer. And it's been known for quite a long time, even though we didn't necessarily understand the underlying processes that made them warmer. We've been able to measure temperatures for a long time, so we've been able to sort of notice this. I'm sure even Luke Howard wasn't even the first person. There's probably earlier examples throughout the world. So what do cities do? Well, they modify this energy balance. They add complexity and they add sort of additional processes that sort of move this energy balance slightly off, balance, by sort of modifying the way that the atmosphere and the radiation interact with the surface. So let's look a little bit about what makes cities different. One thing is they reduce natural surfaces. So we spoke a little bit earlier about how some of the energy that goes into the surface goes into evaporating water. Well, if there's much less water, you might know that concrete, for example, absorbs much less water than soil. Much less energy can go into evaporation of water. So that energy has to go into some of the other processes. We have material properties that we're changing. Concrete and also many of the other materials that we use for our buildings, our infrastructure, often can hold more heat. They often are also darker, so they absorb more of that incoming radiation rather than letting it reflect off. We also modify the geometry of the land. Buildings are not very typical shape found in nature. We're suddenly adding all this complex geometry that creates shadows, that creates wind tunnels and stagnation points in the wind flows. And we also introduce heat generation. We through the marvelous discovery of air conditioning and by the concentration of so many people in such a small place, we are suddenly converting part of the land into generating heat, essentially moving the heat from inside of the building envelope to the outside. And it's sort of like a heat generator of sorts, as far as the atmosphere is concerned. So, and not only do these processes that, or things, little details that we're adding to the land surface sort of change that incoming and outgoing radiation, some of these actually also depend on temperature. So it introduces additional complexity into the system by introducing more feedbacks. Similar to how at the global scale, when it gets warmer, more water vapor evaporates and makes the atmosphere more opaque or able to hold more heat. The warmer it is, and let's take air conditioning as an example, the more energy we have to use to cool the inside of our buildings, and the more energy our buildings store, which means that we are outputting more heat out into the atmosphere, which in turn makes the atmosphere a little bit warmer. So we get some of this further feedback effects that are depending on the temperature. So you can sort of start forming the picture in your head that as things get warmer, you're sort of feeding or adding fuel to this relationship here. And we can see that in some studies that have been done in New York City. What I'm showing here is the result of a set of simulations that attempted to sort of break apart how different parts of the city and the land surface contribute to temperatures over New York City during a heat wave and outside of a heat wave. So that blue curve there that you see there, it's essentially the contribution to temperatures from that very large heat wave event that comes from the atmospheric blocking I feel like Susan set up my whole presentation perfectly by introducing all these concepts. You get this sort of a daily cycle, at minimum at night, and it gets really hot during the day, up to 6 degrees Celsius or Kelvin into the middle of the afternoon. Outside of the heat wave, where you get that dashed red line, the city makes the air around it a little bit warmer, to the order of 1, maybe 2 degrees in some parts of the year. However, during the heat wave, it gets kicked off the charts. It's essentially almost as much as the heat wave itself contributes in New York City during parts of the day. So there's that sort of feedback loop that I was alluding to earlier that we're starting to sort of uncover through these sort of simulation studies. And actually, I'm going to go into a little bit more detail a little bit further on this simulation study. And there's been quite a growing body of work quantifying. I think the first study called it synergies between cities and extreme heat. They've done studies in Beijing, Shanghai, Athens, all across the US, and there's more every day. And sort of quantifying these sort of synergistic or additive nonlinear effects on how cities modify the air around them. So I've been focusing a lot just on cities and how they modify the air around them, and sort of taking the example there of a heat wave. And the reason I like heat waves, because it's sort of like introducing a view of future climate temporarily. You have this period of extreme heat, and it sort of adds fuel to some of these processes in a way that might be similar to how by the end of the century, the general summer climate might sort of be adding fuel to these processes. So let's talk a little bit about how that can go in terms of the broader climate change. And we're going to start first by introducing what we call the scale problem in climate modeling. Essentially, global climate models have very coarse resolution, between 100 kilometers, 200 kilometers. So you only get information that close to each other. Now, as you all might know, New York City it's way smaller than 100, 200 kilometers. And what I'm showing there is an example of one of those models over the Northeast United States, showing the daily maximum temperatures towards the end of the century. And you see very clearly that all of that sort of 31 county area is more or less essentially just one block of information. And as we just were discussing, cities modify the surface in many ways. So there's a sense that this sort of coarse level information might not be enough to fully understand the impacts of climate change on cities. So one possible solution to this issue is what the scientific community calls regional climate modeling. So essentially you take a mathematical model very similar to the global one, but you run it over a limited area. That area can be 100 kilometers alone, or maybe a little bit more. And what that allows you is, with the computers that we have today, is run information at much finer resolution. So this example here is from a set of simulations we did from a heat wave in New York City in 2010. And it actually allows us to get a lot more detail. You see parts of Brooklyn and Queens. These are daily minimum temperatures during a heat wave. So you see parts of Brooklyn and Queens sort of get a hot spot. You see sort of the temperatures as you get outside of the city getting cooler and cooler, sort of alluding more to that sort of heating effect of cities. So we can now, like with these models, sort of add a lot more detail that we are not able to get from the global climate models. And we're able to run these models all the way into the future, just like we do the global climate models. In fact, they use the global climate model information as a sort of constraint to tell what the boundaries of the little finer scale simulation should be. And not only that, but because we're running these models at much higher or much closer spacing, we are also able to resolve processes that we were not able to resolve before, namely and chiefly in cities, cities themselves, the effect of buildings. So right now, sort of the state of the art in these models of sort of city and the weather model or climate model is called the building effect parameterization, which essentially approximates or estimates the effect that buildings have on how radiation moves through the building canopy, how winds are affected by the building canopy, and not only that, but we can also treat buildings themselves as sources of heat that is depending on that atmospheric temperature. So we're able to model that air conditioning effect as well dynamically with the changes in the atmospheric conditions. So going back to the same simulation where I showed that sort of time series earlier, these are sort of the maps that come out of separating each of these effects. So sort of unsurprisingly, if you just consider the urban land surface, it's got a pretty positive signal. Essentially, the deeper the red, the stronger the warming signal. And during the heat wave, that sort of gets intensified, as the panel to the right shows. A little bit surprisingly, is that if you add the buildings to the land surface, it kind of has a cooling effect. It was a little hard for me to understand this at first, but I guess it makes a little bit more sense if you think about the urban land surface as a slab of concrete, and then we add the geometry to it. Well, a slab of concrete is almost always going to be a lot warmer than a rough piece of concrete, because you have shadowing effects and stuff like that. But the interesting part is that once you have a heat wave going on, the contribution of all of it together has an additional effect, what we call a nonlinear effect on the temperature field. In fact, it adds somewhere between 1 and 2 additional degrees Celsius to the air around it. So it's almost like the fact that we have the city and the fact that we introduce a heat wave to it makes that process where you have air conditioning and heat storage be more and more important, because it introduces more energy into the atmosphere that kickstarts that whole sort of energy feedback loop that we were talking about earlier. So something we did is we ran the same model for a set of years towards the middle and the end of the century, and computed how heat waves might look like, given all this information that we have and how cities modify the physics or the processes over the surface. And we found that the characteristics of heat waves don't just have one value over the city. In fact, they vary quite a lot over different parts of the city. It might be easier to see if you look at the bottom right for the 8.5 scenario by the end of the century. Closer to the coast, you have less and fewer days, and as you get throughout further inland, you start getting more and more heat wave duration days. So these tools allow us to look at how climate change will modify the climate of cities at a new level of detail that is not quite captured in global models. And because we are including the effect of buildings, that sort of dynamical cooling load versus atmospheric exchanges of energy, we are also able to sort of estimate how the energy that we need to cool the inside of that building envelope will change. For example, we found that towards the end of the century, we expect to see almost double or more of the need for cooling that we would see when we compare the high emission scenario versus the medium emissions. But we also see that where we see the highest increases are on the coolest days. So there's sort of a loss of those coolest days of summer. So we're going to have to see more and more days where energy for cooling will be necessary. So to sort of cap it off, I like to also talk a little bit about what those impacts mean in terms of not just like temperature and just abstract cooling load increases, but also people. because at the end of the day, it's people that live in cities, higher concentration than average of people, and that is growing at a faster rate than non-city populations. As per the last decennial census, cities are growing at about 3% higher rate than the rest of the country. And right now, about 80% is residing in what the census considers metropolitan or urban areas. So where do people experience heat most often? Well, people spend a whole lot of time indoors. This study from some colleagues placed sensors indoors at a bunch of houses in Harlem. And what they found, that red curve is the outdoor temperature, which follows that sort of like very traditional cycle of cooling in the evening and then warming up in the afternoon. But during a heat wave, what you see is that because of that energy storage in buildings, the temperatures really don't change that much indoors. So there's like an added level of risk of being exposed to high temperatures for longer periods of times in cities. In fact, when we did our similar simulations of indoor climate, we found very similar results. Once you introduce the climate change signal, what we found was that the amount of hours by the end of the century would almost triple compared to a typical summer in the present. And this is mostly because of that lack of like cooling off period indoors. And that variability that you see, that has to do with the way the morphology of buildings and the fact that we have a sea breeze in New York and stuff like that. So as you go further and further inland, you have more and more of that heating effect. And you might say, well, no problem. We'll just put air conditioning in everyone's houses. Well, it also means that it will cost more to operate your air conditioning. And so we sort of computed what the change in air conditioning use will be between the present and the future. And you see that areas, or actually what we computed is the burden in terms of medium household income. And we do find that the areas where that have low income have the highest burden, unsurprisingly. But a little bit more surprisingly is that the areas, those same areas also experience the highest level of increase in their energy use. In fact, if you want to look at it in terms of the monthly income and that percentage change between the present and the future, as your income goes down in New York City, you're bound to see a higher percentage increase in what you pay to operate your air conditioning. Now, this is my sort of final slide. I know we're sort of at the time limit, so I won't run down through it, but in general, there's a lot of these sort of feedbacks that happen in cities, and climate change is essentially adding fuel to some of them, making some of them more important than others, and that can lead to sort of a widespread level of impacts felt in very unequal ways across different populations. So I'll leave it at that, and yeah.
Yeah, thank you so much, Louis. I really liked how sort of Susan's presentation set up a lot of the things you dove into in a little bit more detail. That was great. Next, we have Peter Marsters. He's been doing a lot of great work on carbon tax research and gets into some more of the policy side of things. And I think that's a great, when I immediately think of quantifying climate change or data and things like that, you know, I'll think about heat, I'll think about precipitation, things like that. But sort of the carbon tax side of things, I think that puts like a really interesting spin and is, you know, equally is important. And the policy, I think, is really going to be driving stuff in. So I'm really excited to hear more about that right now.
Cool. Thank you, Mike, and thank you to the rest of the GreenHomeNYC folks. It's very exciting to be here and glad to see, like, you know, organizations and events like this continuing. It's heartening. Okay, I'm Peter Marsters. I'm a research associate at Columbia University's Center on Global Energy Policy. And to kind of wrap up tonight, I'll be talking about kind of quantifying emission projections and how we think about like emissions going forward, and also talking about kind of walking through an example policy, in this case a carbon tax, and seeing kind of quantifying what are the impacts both economically and in terms of emissions, which is one of the big things we end up caring about. And then finally, which ties in more to kind of the local New York City specific issues, is a new project we're working on that's trying to take some of these emissions projections and some of these policy costs and tie them down to the household level. Really try and understand what are the costs to implement such a policy, who's going to be made better off, who's going to be made worse off, how do you ensure equity across the income distribution. And yeah, so carbon taxes aren't traditionally the most exciting things in the world, but I think hopefully this one will counter that traditional sentiment. All right, so the Center on Global Energy Policy, we're a research institution, we're nonpartisan, non-advocacy, so we try and sit behind, as objective as possible with all the caveats that come with that word. Here's what the most up-to-date models and data tells us about emissions and certain climate policies in the United States. Where I sit currently, we largely focus on carbon taxation, but we also look at things like heat pumps and clean energy standards and renewable energy kind of policies. So not exclusive, but it will be kind of the focus of tonight's talk. I'd like to start out by discussing just kind of what tools and how do we think about emissions going forward. You saw in the previous talks the RCP scenarios, and those aren't, as Liz said, exactly emissions outcomes, but they're highly correlated, as in if we have more emissions, we'll likely be on a higher RCP pathway. And so where we sit, what we want to do is try and, as best as we can, project what are emissions likely to be in the United States. We largely focus on the United States. And we use a lot of energy modeling tools to do that. One tool we use is called the National Energy Modeling System. It's put out by the Energy Information Agency, and it's this big, complicated, too granular kind of energy model that even goes down to say, oh, what's the size of a trunk in an electric vehicle, and how does that impact a buyer's preference? So all that's to say is, like, these are very super detailed, highly refined models, but there's a ton of caveats when thinking about how these project. I think the most real example now is kind of looking at here's the IA's latest projections, and this does not include anything regarding the impacts from COVID-19. So prediction is hard, especially about the future. So anytime someone's kind of like giving you some of these models, all the grains of salt in the world are probably necessary. But anyway, they can tell us some useful things. And starting out here, this is the reference case, and you can see it's slightly declining to 2030. We stick in kind of the near-term space just because we feel like trying to predict energy prices, costs of technologies, all these other issues out farther just becomes less and less reliable. You look 20 years ago at what people were predicting solar prices to be, and they were magnitudes off. And so we stick to kind of 10-year windows to kind of see, like, hey, if you were to implement XYZ policy, what would the outcomes be? But if we take a snapshot of policies as they exist in the United States today, emissions are relatively flat. Power sector emissions go down slightly, so electricity, you know, industrial, transport, and building emissions, if we, you know, don't have any intervening policies, are likely to hold steady, increase slightly. Nothing at the kind of level you would need for zero emissions. You know, you don't stop warming until you stop emitting, and this is not a pathway to hit any sort of net zero target. So we talked a little bit about like some of the caveats in modeling, but I think what's here is it can tell us what levers and how hard to push them. You know, I think looking at the carbon tax example, which I'm going to show you shortly in the next slide, there's a pretty clear sign of what can change in the next 10 years and what will require other policies, interventions, kind of other ideas to change. So what we did to kind of get into the carbon tax example, we took a bill that is currently in Congress. It's proposed by Ted Deutsch, and it is called the Energy Innovation and Carbon Dividend Act. It is a price on carbon emissions as well as HFCs. So, you know, the gases that are in your air conditioner and your refrigerator, that rises over time to getting to about, you know, $115 by 2030. So every ton of emissions you emit in 2030, you'll pay to the government $115. You multiply that price out through the entire economy, and what happens is lower carbon options become cheaper, and so people choose them. Through our modeling, you know, this reduces U.S. emissions by roughly anywhere from 37 to 42%, depending on certain assumptions. We leave a wide band for kind of different assumptions about energy prices, different assumptions about economic growth, but that is on the path to Paris, and it's certainly a major improvement from current policy. However, a lot of that is coming just from the electric power sector. There is a lot of cheaper existing technologies that we have right now that can essentially replace coal power in our power sector. This happens fairly quickly in the models, which means, you know, kind of it's able to happen today. And, you know, there's a lot of ways you can get there, but the main way is just building a lot of wind and solar. That technology is mature, it exists, there's markets, there's builders, there's workers, it's kind of got everything you need. And that's where you're kind of likely to see the largest emissions reductions in the next 10 years. That being said, if we kind of go back to that first chart, and kind of thinking about where emissions reductions come from, we can look at here all the other emissions, the industry, the transportation, the buildings, and a carbon tax doesn't really impact that all that much. You can think of this easily, you know, a $50 a ton carbon tax, which is relatively significant. You know, it would be more than currently the EU pricing and currently the California pricing. It raises gasoline about by 44 cents a gallon, which is significant, you know, but it's not enough to change people's behavior enough that they will go out and say buy an electric vehicle. And so you really have to start thinking about like complementary policies. You know, not one of these is a silver bullet. And so we kind of put this chart together looking at what policies would be complementary to this, kind of like looking sector by sector, what else do you need to do, and what's kind of like already been covered. And a lot of that is kind of, either like investing in public infrastructure for like mass transit, really improving building efficiency. That's from our research, we found a huge potential for reducing emissions by 2030. Getting rid of fossil fuel subsidies, air pollution regulations. All of these can move the needle, the emissions, down significantly by 2030. And so we've got some other work focused on those that you can go check out our website, and hopefully it's easy to navigate and easy to see. So that's kind of the emissions side. We also look at the cost side, putting a tax on economic activity will cost people money. That money goes to the US government, and depending on which carbon tax bill you're looking at, can be used in a whole bunch of different ways. This particular bill elects to give that money back in just direct cash payments to households. They gave a different amount for adults and children, but regardless, if you are an eligible US taxpayer, by 2030, you're looking at getting about $1,500 a year per person, and half that for children. And we kind of want to say, okay, so you've got the two sides of this coin. One, you're putting a tax on the US economy to encourage low carbon activities, but you're also giving money back to households to protect those that can't afford those price increases. And so we wanted to kind of like see how that balanced out. And it turns out that question really depends on two key things. First is how much money you make, and the second is where you are in the country. For the first issue, wealthier households spend differently than poorer households. Low-income households may have more trouble affording the end cost increases that come from putting a carbon tax on the economy. So we wanted to think through how that actually gets passed through to the end consumer, to the household. Where the cost goes, who's paying them? The big takeaway is that a lot of the price won't be through energy bills. That's where it'll be most visible. That's where people will find it, most kind of salient and be able to kind of interact with it. It's like you see gasoline prices go up the next day after a climate policy is introduced. People tie one and one together pretty quickly. Where most of the price increase will come through is through goods and services. Everything we do, everything we consume largely has a carbon implication. Let's say I put a carbon tax on coal. That coal is then therefore used to make steel. Putting a tax on that coal used to make steel raises the price of steel, raises the price of a vehicle or chair I buy that contains steel. But it does it in such a minute way, it's unlikely to be noticed. But that is where most of the costs will be passed through to households. And so we combined two sets of data. First set is estimating how much households, how much energy they consume, and then we can just apply, say, this household at this income level from survey data drives this amount for this year. Therefore, we can estimate how much gasoline they consume, how much carbon price will they likely pay. And we can also use regional modeling through what's called input-output modeling to estimate, okay, so you put a price of on carbon on coal, that gets passed through to steel, then that gets passed through to the vehicle, we can figure out roughly what the end increase of price will be for that consumer of the vehicle. And the takeaway is that, you know, because most emissions don't come from the household level, it'll be from kind of increase in price of goods and services across the economy. And so this chart shows roughly in 2025, so kind of taking into account how much emissions are reduced, as well as kind of what energy system changes happen, we can estimate what the average payments are. And they range, you know, for low-income households, it turns out to be more on, you know, things like electricity, natural gas, fuel oil, gasoline, and that's up to $1,000. But for, you know, high-income households, that's about, they would pay an increase about $4,000 in increased prices. And we can also see that geospatially. So we can get very detailed kind of census tract level data of where this carbon is being consumed. And there's a couple takeaways. The first is that this is a story about wealthy households consuming more carbon, and or so they, a lot of the red areas you see are a combination of two things. It's wealthy suburban households who drive farther, as well as they have higher incomes, so they buy more stuff. That stuff contains more carbon. I mean, it's kind of, it makes sense, but like now we've got a good picture into where and how these prices might increase. The other thing to mention here is that a lot of this is driven by kind of non-household choices. You know, if you live in an area with a coal-heavy power sector, in putting a price on carbon will increase the price of electricity for everything. You know, it'll increase the price of electricity for the 7-Eleven that you go to, or say, you know, building a new house, that gets passed through. So there's kind of compounding effects if you live in an area that is higher carbon consuming rather than lower. And taking a like more zoomed in view of that, you can kind of see that with vehicle emissions. This is how much people drive, and like clearly like folks in the city who have access to mass transit and like, you know, urban planning choices that make it easier for people to get where they need to be, they see less vehicle emissions, and they will see less price increases from a carbon tax. Then we took all those price increases, and we gave, as the policy is modeled, gave a certain amount of money back to each of the households. So the Energy Innovation and Carbon Dividend Act said, okay, we're going to raise the price on carbon intensive goods. We're going to take all that money and give it back in equal lump sum payments to households. And this is roughly how the net impact of that works out. So low income households, because they pay less in the tax, but receive more in the dividend, come out positive. This is on average, so every household is slightly different. And that it works up to about $100,000 in annual household income. So that's not individual income. On average, they have a slight benefit from this policy. They will be receiving more money from these checks than they pay out in increased taxes. All that money that they are receiving comes from higher income households. And so there's a wealth transfer if you organize a carbon tax policy this way. And you can also see that geospatially. Here, this is again the energy system in 2025. And blue areas are areas that are likely on average. So this is a view of all households, not just wealthy or lower income households. they will be receiving money from a policy like this, and the red households will be paying money. And there's a lot of kind of like equity and distributional and fairness issues to think about, and like pointing to that is, you know, North Dakota, which is a very carbon intense economy. There's a lot of oil and gas, a lot of mining. It's very rural, it's very cold, it's very has large transportation distances. Will likely pay a lot more than, say, you know, New York or California or all these other places. And you know, we again are a non-advocacy organization. We kind of want to make these issues aware, and policymakers can decide what best to do with them. We will make the caveat that a whole lot is not captured here. There are communities that will be impacted by things like, you know, clearest would be coal communities who, as coal power goes away, so does a lot of income to those areas. There will be air pollution changes. You know, hopefully as emissions reduce, that will be generally for the better, but it also shift emissions from certain communities to others. And the final point I think I want to make is that, you know, these issues aren't necessarily unique to a carbon tax. For a lot of low carbon transitions, there will be societal costs. It's, you know, currently more expensive to own and operate an electric vehicle, depending. And so how those costs get distributed throughout society is, you know, likely to follow similar patterns. Certainly not to the same degree, and certainly not in the same areas, but really thinking about which households, where in the country, are you doing enough to make sure that, like, folks who can't afford any increases in energy costs or carbon costs, that they are protected from whatever policy you happen to choose. And with that, I think I can wrap up, and happy to take any questions.
Yeah, thank you so much, Peter. That's a whole other layer of information there that I think it's especially new to me. It's something I haven't had the chance to jump into as much, and I guess I got a lot of homework to do. Right now, we will jump into some Q&A. We've had some questions come in, and feel free to drop any questions you may have in the chat box here, and we'll ask them of our panelists. Jenny, want to take it over from here? Or change of plans here, guys. I apologize. I need to make sure that I'm covering these bases before I forget. First of all, you know, obviously thanks to all of our great speakers, and we have an event coming up, another virtual webinar on sustainability for non-STEM. I think that's going to be a really great event. Here we spend a lot of time on the data, a lot of more of the scientific side of things, and I think that for people that want to become more involved in sustainability, that didn't necessarily have that STEM background, this is a great opportunity. Also, for in terms of volunteering, we had some questions come in about volunteering. Visit us at GreenHomeNYC.org for more information. Also check out everybody's organization online. Let me see here. Jenny, do we have any of those questions?
Yes.
Drop?
Sorry, I think I was on mute before. Big thank you to all of our speakers. I think that was really incredible that we got to fit in so much in such a short amount of time and hear from you all on such an important issue. Some of the first questions that have flowed through are for Susan. This first one is from Zoe Kaufman. So the question is, how is it possible that New York City and New Jersey have such different levels of sea level rise? Is gravity really affecting these two areas so differently?
Well, that's a really good question. And in the long run, I don't think those numbers are that different if we compare them. And to be quite honest, I'm not a total expert on this. I just like presenting the data. What I do know is on the Jersey coast, for example, there are parts that are on bedrock and there are parts that aren't. So in Bayonne, New Jersey, sea level's only risen 12 inches and Bayonne is on bedrock, but in Atlantic City, sea level has risen 17 inches, and that's partly because of erosion into the ocean and all. So these things, it all depends on the geology of the area, and quite frankly, I'm not a geologist. So, but that's a good question, and you can look into it more like that, but where it has a lot to do with the geology.
Okay, great. Thank you so much. This next question is from one speaker to another. So from Peter to Louise. Louise, what are your thoughts on painting roofs white?
Oh, thanks. So it's certainly a solution. We've done some simulations on sort of like an aggregate effect on New York City of sort of white roofs or increasing the reflectivity of roofs. We found that it doesn't really change much in terms of ambient temperatures, and the effect decreases the taller and skinnier the building is. So essentially, the less the roof is part of the surface of the building, the less important it is. And we got a lot of areas in New York that are like that. What we did find is that in sort of shorter, squatter, more residential areas, shorter, squatter buildings, I should say. It does make a good deal of difference in terms of energy consumption for air conditioning and in particular in the summer. I think we saw something like 10-15% reduction on those type of buildings and like less than 5% in very tall buildings. So yeah, it's similar to green roofs and maybe cheaper to implement, although you get less of an effect from the evaporation that the green roofs adds.
Thank you.
Yeah, well.
Thank you. Okay, next question is for Peter. How is the 2030 $115 price established? Is it in any way related to the kind of cost it can save if we prevent global flooding and halt of the economy as the century will grow old?
Very good question. In some ways, yes. In some ways, no. So I think the question is referring to, from a pure economics perspective, you want to set the level of a tax equal to the amount of damages it causes. It's what's known as like the social cost of carbon, which takes into a whole lot of assumptions of, okay, how do we value, what are the damages likely to happen in the future? How do we value those? And what, you know, at the end of the day, are we willing to pay to prevent those? The short answer is there's a lot of estimates that range widely from, you know, $0 to $1,000. And it gets down to the issue of like, there's not a lot of certainty as you go out farther, and that increases the range of possible costs of climate change. So what most policymakers end up doing is taking some variation of, there's, for example, 3 main damage models that estimate the cost, and then they just average them together. That's one school of thought. Where this particular price, I believe, comes from is a rough estimate of like, okay, we want to scale this in slowly. It starts at $15 a ton, which shouldn't have a whole lot of economic disruption. And what will actually get emissions down? And that ends up being kind of a process of like reading energy model results saying, hey, you know, you can get, in general, like you can get a lot of emissions with a small carbon price. You can keep increasing carbon price, but you will probably see less emissions just because, say, you know, to the point of those other sectors like transport or industry are just much more expensive to abate in. So long answer short, it is not in the range of the social cost, or it's not directly related to the social cost of carbon in this case.
Okay, thank you. The next question is another one for Susan. What is the expectation of damage by the next hurricane similar to Sandy? Susan, I think you're still on mute.
You go. I don't have a number to give you on that. I'm sure that there really hasn't been done, we haven't done much actually on the coasts to protect people in their homes from another Sandy. If the sea goes 12 feet high during a tidal surges, then you know, those homes that they've raised, that's good, and I know that they've worked hard to put protections around things like power plants, and they have put a lot of money into a lot of infrastructure, but we haven't put that much money into residential things. You can go and look at flood New York City. You can look at the FEMA. You know, if you live in a flood zone, we're identifying that. You have to have flood insurance. But how good is flood insurance when your home goes away due to a big wave? So I don't have a number, but if I were a betting person, which I'm not, I bet we're gonna have damages of at least the same cost that we had. Hopefully less losses of life, because people will be more aware of what the damage could do and will evacuate, hopefully. So, thank you.
Thank you. I don't think I'd bet against you on that one. The next question is for any speaker who wants to answer. Do you see the recent changes in behaviors and activity, commercial, industrial, et cetera, due to the COVID-19 shutdowns as helpful or unhelpful towards better understanding climate change trends? And what can we learn from this period? And I mean, if all speakers want to answer, that's okay too. We can open it up.
Happy to take a stab. First and foremost, with you know, all issues, the uncertainty here is a lot larger. I don't think I've seen a lot of great estimates of how tough this is going to be from a kind of like economic growth, recession, depression point of view, all of which, in my personal opinion, I think makes things harder to decarbonize and makes things more challenging. While you will see a pretty significant but temporary drop in emissions from people driving less and flying less and all the like, it is not the structural institutional change you need to get to net zero emissions. And, you know, it's going to be expensive to, in the short term at the very least, to like mitigate some of these emissions. And I believe it's a lot easier when people have jobs and are fully employed. So that's my 2 cents, but with the large caveat uncertainty.
Luis or Susan, do either of you have anything to add?
I think we have seen some decreases in some, certainly some some of the sources of energy demand, for example. But as far as I was aware, there have been some that have been sort of staying more or less flat or seeing a very sort of small decrease in terms of energy consumption. And in residential use, you actually see an increase of energy demand in some parts of the country, especially as we go into the warm season. So yeah, I think it's you see like maybe the sky's clearing up and some of the emissions have come down, but without that structural change, it's sort of a very temporary effect, like Peter was saying.
Yeah,
Oh, go ahead.
no, it's just unfortunate. We don't have the leadership. We could come out of this in a different direction than we're headed. And that's very sad. And unfortunately, I think the way the attitudes are in this country, we're going to see a huge spike when this thing is over. It really isn't. A lot of industry is down, but a lot of residential use is up, as Luis said. So it's a nice dip, and the air is definitely cleaner because some of it's the right kind of pollution that's gone, but nonetheless, unless we do something, I'm hoping some other countries are going to be more forward thinking than we are as we end this. I heard the term the great pause, that's what this virus is, and this quarantine, and I really like the expression. So as we wake up from this great pause, I think that we're not going to see a reduction in emissions, especially in this country.
Thanks, everyone. I think that's all we have for questions. So Mike, I'll turn it back over to you.
Yeah. Again, thank you guys so much for joining. I think we'll keep the room open for a little bit if people want to kind of mingle around. Normally we'll, in person we'll have, we'll go out and grab drinks and sort of talk a little bit more. If anybody wants to stick around, feel free. But otherwise, thank you guys so much for joining, for the speakers. I know I personally learned a lot, and I've got a lot of homework now, I think, to catch up on. But again, thank you guys all so much, and hope everybody's safe and healthy. Thank you guys.
Thank you. Yeah.
Hey, if you want to unmute folks, Mike, I'd say go right ahead.
Oh, yeah.
Thank you very much. I'm going to have to leave the meeting. I'm late for another meeting. So thanks so much for having me, and best of luck to everyone, and stay well.
Thank you so much.
Thank you all.
Thank you. Great talk.
Wonderful.
Hey, Louis, I'd be curious to follow up on the white roof stuff. I just remember I don't know, maybe a decade, I don't know, a while ago, everybody was kind of all about it and saying it was super effective, cheap way to kind of, it's, not necessarily mitigation, but geoengineer some stuff. I was just curious on is that out of fashion, or is it still worth pursuing from a policy perspective?
I don't think it's out of fashion at all. But sometimes these technologies kind of have a big splash in the news, and then everyone's talking about them for a while. But I think they're still actively implemented, and they are a relatively inexpensive way to reduce energy use in the summer, and also reduce indoor temperature conditions too. So yeah, they're definitely still. It might have even been included in one of those recent New York City local laws as part of the required technology efficiency increasing technologies. Don't quote me on that. I'm not sure. I know they mentioned green roofs for sure, but white roofs might already be some part of that regulation.
Gotcha. Huh. Yeah. It's I mean, I am not a homeowner, but if I were, would I want to paint my roof white?
Well, I mean,
You have the tool you need.
Yeah.
You need to scrape it off.
I don't know. I'm not even aware of the expense of it. I don't know what so I live in New York, so I very unlikely statistically to be a homeowner either. But yeah, compared to like something like a green roof, which is another like much touted technology, it's way cheaper than although it provides fewer benefits. Like it doesn't have the stormwater retention benefit and stuff like that. But certainly for places that get hot in the summer, it's certainly in use right now.
For sure.
Ooh, it's all that stuff on the BEP and all those different sort of effects. It was really cool to hear. Kind of reminded me of sort of like what is it for the wind turbines, the wind roughness or something like that. Kind of made me think back to those days, learning about that stuff. But yeah, all the turbulence from the buildings, the radiation, so much stuff that I guess you wouldn't normally think of, and so many different variables that go into it.
They actually have been putting wind farms in the model in the past few years. So I mean, in a way, it's a similar sort of type of effect, right? It adds some turbulence to the atmosphere and stuff like that, but maybe a little bit more complexity because turbulence is crazy complex. But yeah, it's sort of a it's sort of like one of the super important advances, I think, in regional climate modeling is including the city and being able to quantify all these sort of different exchanges. It's I think it's fantastic.
Policy thing that, sorry, go ahead.
Go ahead. No, go ahead.
I was just going to say, I guess my wonderings tend to be a bit more local to some extent, especially knowing more of the policy things that have been happening around this, for the city and state, like the congestion pricing plan, for instance, which, is supposed to be a pretty big deal and go into effect at the beginning of next year, even though it seems like the governor's pretty clearly slow walking it because he hasn't even put together the committee that was supposed to make further decisions on fleshing out the plan and the pricing. So it's like, I kind of wonder, actually, is it more likely or less likely coming out of this that the governor may not want to, the mayor might want to, but as we get out of the whole COVID situation, the worry is what's going to happen here, what's happened, I think in Wuhan in China, where that everyone goes into driving cars and kind of ignores and avoids public transit. I don't know, I'm just trying to sort of muse about what seems more likely to be some of New York's moves in that respect as we get later in the year.
Process.
So and how many of those things are gonna?
Go ahead, Mike.
How many of those things are gonna become just sort of society in general, or what are those major trends gonna look like? Is there anything that's gonna stick around? Or I imagine there are a lot of different ways that people are gonna be living now.
And for that one,
and I'm wondering, I'm also curious what you guys think about sort of anything that you think sticks
of approval
behaviorally.
Of approving authority,
Yeah.
and then parentheses, president.
I have no idea, but I also feel like people forget easily, I suppose. The kind of one theory of everybody's going to be kind of working from home and working remotely, and everybody's going to go move to suburbs or somewhere. I don't know. I was like, A, that's very few people can do that, and B, I think a lot of people are going to be I kind of miss the office and people, and go right back into the old ways. The public transit thing, I think, is super interesting of how you open that back up, and with everybody having it. Yeah, it was, who was that? Gregory, right? Yeah, saying everybody's just going to want to drive, and that's, it's going to be crazy.
Yeah, it kind of seems like the mayor would want to push to make that happen, because that would be one of the things that would keep a resurgence in that way from happening.
Yeah.
As, some might argue the city, or city or state, or someone's trying to start to break car culture here. Yeah.
Do you all have any of the slow streets around? I don't have any in my neighborhood, but curious if anybody's been out and about of the pedestrian streets.
I've been following it, but I haven't gone out to any. Yeah.
I'm like a little bit curious what happens to the numbers of the suburban versus the urban when the suburban people don't drive as much and public transit keeps going, because that's like what's happening right now. So I'll be curious to see when there's a little bit of data about it. But
For
I
sure.
was wondering if any of you had actually seen the new movie Planet of Humans, and if you had any basically his main claim was that sorry for my noise that my kids are doing, but he's basically saying that they're like the way that carbon is calculated is wrong, and basically people are doing activities that are supposedly carbon saving, but they're not. So anything that you have to say about that?
I watched part of it. I don't agree with a lot of it. But I think there's this contrast where it's like, green, clean energy is just that. But, it requires space. It requires a big industrial, kind of foundation and background. And it requires, putting a lot of windmills all over the Midwest and putting a lot of solar plants all over the Southwest. There'll be serious kind of human influence changes. So in that regard, I think they're I don't think people have fully kind of digested what a net zero transition could look like. I think it's going to require a lot of the traditional kind of wind and solar have their own issues, I guess, is the long story short. But curious to hear other thoughts.
Yeah, good point. Thank you.
Sally, I haven't seen it yet, but I've heard it misrepresents things somewhat, so I kind of didn't feel very.
Yeah, it's a little bit depressing just to see, but I think I like to be audited. I think that it's always good to look at what you're doing and see how someone criticizes it. So I don't object to that.
Yeah, I think that's the issue is how if it's weaponized in unfair ways, I suppose.
Yeah.
Hey Peter, I'd like to get your thoughts just in general about working with so much of the policy stuff. Just the little bit I've experienced in the past couple of years, it's just painful. The time it takes to move things along, getting people on board with things. How do you deal with that?
Yeah, and I think there's a big difference between federal policy and local policy. And in some ways, I think because local policy can actually happen and do things, it's a whole nother level of complicated and real that at least for the last 4 years, we didn't have to deal with at the federal level, because it's you could propose whatever you want and there weren't any real consequences in it due to the political landscape. That everybody was kind of very excited for a change post 2021, and people ramping up for a big climate package at the federal level. That whether that goes hand in hand with a big COVID stimulus package, I think is still to be determined. I don't know. And yeah, in general though, I think local and city politics and even state politics are that's where it's at, and that's where you're most of the action has happened.
Yeah, that's a really great point.
Yeah.
Oh yeah, that's all I got, you guys.
So something I noticed is that one of the big worries, especially with this COVID situation, has been sort of the upcoming summer, because people are spending more time indoors, so they're probably not at work where there's probably air conditioning, or if you don't have air conditioning, you can go to a cooling center, so that kind of doesn't quite work when you're, socially distancing. And something that happened that actually surprised me a lot is that the city got, I don't know, like 75,000 air conditioning units to several, mostly NYCHA buildings. And I was actually surprised because this is actually a policy that's been trying to be pushed for many years by the Department of Health folks. And because they've shown that, if you have air conditioning, you have much lower likelihood of suffering the ill effects of heat in the summer, or much lower likelihood of dying and stuff like that. And just by pointing a finger and sort of exacerbating that upcoming vulnerability, it sort of prompted into action. Even though we're not in the hot season yet, it sort of forced sort of the city to think about these things and force effects on policy that I've seen recently too.
Yeah, I don't know. It's interesting to see the very small, or like silver linings out there, but which I guess that's like in all this chaos and terribleness, it's like, oh, there are like opportunities, I guess. Yeah.
I think the biggest thing is just like the way people mobilize, like, right? That we're talking about big changes that need to be made, and people can make them if they want, if they feel the urgency to do that. So
right.
I think that's a big point. I wondered if any of you just have a wish list of any data that you would like to, like, unrelated to COVID, like if you had more data, you would be able to do more. Like, what would you like? Is there anything that you would like to get better data on?
I mean, for me personally, it's like it's going back to like the behavior changes. Like, one thing these models don't do well at all is capture people's behavior changes, which is like so much more than just the sticker price that they see. And so seeing data on like, okay, you put, say, like an electric vehicle infrastructure charging program somewhere, how much does that like encourage electric vehicle use? All these kind of like, or like you put a whole bunch of money into public infrastructure, like say transmission for renewables. What are the outcomes there? And I find that like, that would be super interesting, but